Hello. So here I'm going to go over the 4 problems that were in week 7, the week 7 worksheet corresponding to homework 6. So this first question this corresponds to homework 6 question 3 on that homework. And so it just asks to find the general solution of this second order homogeneous equation. So here we can see it has constant coefficients. So with one of these problems, we just want to look at the auxiliary equation. And so remember, this is the polynomial in terms of r, where the coefficients match up with the coefficients in our differential equation. And so what we want to do here is we want to factor this. And so I think in this case it factors out to 3r plus 1 squared equals 0. We can double check that. 3r, 9r squared times 1, 6. Yeah. And so remember, this means that this equation has a single root, r1 equals negative 1/3. But we'll say it has multiplicity 2. So this just means that it, if we were to completely factor this into linear factors, in a sense you can think of this root popping up twice because we've got 2 factors of this 3r plus 1 term. And so using this root, when I've got a single root like this corresponds to the general solution y equals c1 plus c2 times x e to the negative 1/3 x. So remember, with the double root there, this is how we write out the general solution. So we still have 2 solutions, but this time the second one we've got c2x e to the negative 1/3 x. And so for one of these, that would be really all we would need to do. And so these problems in general kind of just follow the same pattern. So if you've got constant coefficients like this, factor, find the roots, and we can write out the general solution quite nicely. All right. So the next one that I am planning to go over in recitation is homework 6, questions 5 and 6, but I'll kind of combine them together into just one question. So questions 5 and 6 give you some set of functions. So here we've got f of x is equal to 3x. Maybe I'll write it out this way. F of x is equal to 3x. G of x is equal to 4x squared. And h of x is equal to 7x minus 5x squared. And so what the problems want you to do is show in 2 different ways that these 3 functions together are linearly dependent. One way to do it is to find what you might call the linear dependence relation. That is the set of constants C1, C2, and C3. So that C1F plus C2G plus C3H is identically 0. So that's one way to do it. The other way to do it, remember, is using the Wronskian, which I'll do after this method. So this way, generally if you're given these functions and we want to do it this way, the functions themselves won't be terrible. So you see, if you have 3 functions that look like this, notice f of x just has a linear term, g of x has the quadratic term, h of x has both. And so you can actually kind of just eyeball it and figure it out, because when I add the 3 together, this term is going to have to cancel out this term. So if I let c1 equal negative 7/3, notice then 3 times negative 7/3 plus 7x, those terms would cancel. And so kind of similarly, I'll let C2 equal 5/4 and C3 equal 1. And so put all of this together. This does in fact equal 0. So negative 7/3 times 3x cancels out with the 7x. 5/4 times 4x squared gives us positive 5x squared, which cancels out with the 5x squared there. Your book, so notice that like I can multiply this entire equation by any constant and not really change this. So I think the answer, the solution that your book gave was to clear the fractions. So that would be multiply, and for some reason they're then multiplied by negative 12. So I remember the answer on Pearson was 28f of x minus 15g of x minus 12h of x is equal to 0. And that's just because once we've found these constants, we can multiply them all by the exact same constant and never change this. So that's one way to do it. If you find the constants that actually make this sum 0, then you've proven that these are linearly dependent. Sometimes that's actually kind of hard. As we saw, not really in this case, but in some cases, it can actually be quite difficult to find those constants. And so that's why it's nice to have another way of proving that these functions are linearly dependent. So to do this, we're going to need to calculate the first and second derivatives of each of these functions. All right. Did I do all that correctly? I think so. And so remember, to test this, we calculate the Wronskian of these functions, which is the determinant of this matrix. Determinants have tons of other applications in linear algebra, often towards basically kind of doing exactly what we're doing now. Is one of the most common applications is to determine if we've got this set of equations or this set of vectors actually we might do in linear algebra to determine sort of this independence, linear dependence relation. So this extends beyond functions. But so this 3x3 determinant, I've included on the worksheet one way to calculate this. There are actually multiple different ways. But one way is you factor, in a sense, down the column, first column of this matrix. And you can express this as the sum of a bunch of 2x2 determinants. And so this, remember, maybe I won't write out each one just to save space, but when we've got a 2x2 matrix like this, the determinant is the difference of the And so you would do the same thing with these two. The determinant of this is the difference of the product of the diagonal terms. So you do the, we call this the main diagonal. So the left to right diagonal, you take the product of those two terms. And then subtract off the product of the other diagonal, so the right to left diagonal. And so with this, it just makes calculating this possible. It can get a little tedious, but thankfully algebra is just so much fun. So we can actually now fill in actual values for all of this. And just let me know if I accidentally fill in something wrong. There is quite a bit to keep track of. So that should be the first one. Minus f prime, which is 3. G is 4x squared. H is 7x minus 5x squared. And G prime is 8. H prime is negative 10. And I'm just going to write plus 0 here because f prime of x is equal to 0. So whatever the value of this determinant here is, it's ultimately a function, real number. And since this function is equal to 0, it actually does just cancel this whole thing out. So thankfully, we only have to think about 2 terms here instead of 3. All right, so this is equal to 3x times 8x times negative 10. So left diagonal minus 8 times 7 minus 10x minus 3 times 4x squared times negative 10 minus 8 times 7x minus 5x squared. Like I said, a lot of algebra, but thankfully algebra is just so much fun. So maybe what I'll do is I will just sort of start erasing up top here. All right, I'm going to focus on inside the brackets first. So this is 3x times, this term becomes negative 80x. This would be minus 56 plus 80x if I distribute that negative 8 through. Notice these two things would cancel, so here would actually just be left with 3x times negative 56, which is encouraging considering what we eventually want this thing to equal. So then here, this would be minus 3 times. These two terms multiply out to give me negative 40x squared minus 56x plus 40x squared. And that's very convenient because I get minus 56x. Well, and now notice what we've got. We've got 3x times negative 56 minus 3 times negative 56. These two give me 0, which is equal to the Wronskian. And so whenever this value w is equal to 0, that means the three functions are linearly dependent. So this way is maybe a little more messy to do this, but notice we actually don't need to find the linear dependence relation between the three functions in order to, we don't actually have to find the linear dependence relation between the three functions in order to determine if they are linearly independent or dependent. So that's very nice because, like I said, it can get quite difficult to actually find one that works in general. All right, so let's move on to question 3 on this worksheet. So here we're given a non-homogeneous differential equation along with a complementary solution y sub c and a particular solution y sub p, and we want to find a solution satisfying the initial conditions. So here's the differential equation. Equals 6. The initial conditions were given that y0 equals 4 and y prime 0 equals 25. Then we're given the solution y sub c is equal to c1 e to the minus x plus c2 e to the 3x, and a particular solution y sub p is equal to negative 2. All right. So we know that the solution we want a solution of the following form. Or notice the particular solution here would just correspond to the case where these two constants were equal to 0. And so we want to take this general solution, use these two initial conditions, and find the value of C1 and C2 given these two initial conditions. So be careful here. We do want to add on this negative 2 and work with this, this equation and not this equation. So doing that, we get a few relations which must be satisfied. So if y of 0 is equal to 4, we know that 4 is equal to c1 e to the 0 is just c1. c2 e to the 0 is just c2 minus 2. And we could equivalently write this as 6 equals c1 plus c2. We get now y prime. So we know y prime is equal to negative c1 e to the negative x plus 3c2 e to the 3x. And so since y prime of 0 is equal to 25, we know that 25 is equal to negative c1 plus 3c2. And so now we've got two variables, two equations. Oh, I wanted to circle this one, not that one. Two variables, two equations. We can do a little bit of algebra to solve these. So what I can do is I can actually just immediately add these two equations. So maybe I'll actually call this equation 1 and this equation 2. And so notice if I add equation 1 and equation 2, we get, well, the left side we get 6 plus 25 is equal to 31. The C1s cancel out, which is sort of why we're doing this, equals 4c2. This implies that c2 is equal to 31 over 4. And now we can just plug this in into, I guess the easiest place to plug this into would be equation 1. So now we know that 6 is equal to c1 plus 31 over 4. And so this implies 6 over 4 would be 24 over 4, or sorry, 6 is equal to 24 over 4. So this would mean C1 is equal to negative 7/4. And so a solution satisfying the initial conditions would be y is equal to negative 7/4 e to the negative x plus 31/4 e to the 3x minus 2. So just be careful, with a problem like this. Remember, don't forget about that -2. And these steps, there are many ways to do it. You could do it using linear algebra and row reduction. You could do it using the method I used. There's certainly multiple ways when we've got these two equations to solve for those constants C1 and C2. All right, one more problem. And this is actually going to be very similar to a problem that we worked through last week. We're going to use reduction of order method again. I think this is good. This homework has 2 of these problems. I found working through the homework problems that this tends to be, at least algebraically, the most difficult problem. Just because, well, algebra's a lot of fun, but it can be very difficult sometimes. So we want to use reduction of order, and so I described this method, like I said, in last week's video and on last week's worksheet, so I won't go too in depth. We'll kind of just write out the equation and sort of just work like we, in this problem, I'll work like we sort of know all of the details to how this method works. If you want to see those details, of course, they're in the last video and on the last worksheet. So we want to use reduction of order to solve the following. And like I said, this has tricky algebra kind of throughout, so if you see me make a mistake, just raise your hand and say something and I'll stop. We want to solve this, given that x is always greater than 7/4, so on this particular interval, and we know one solution to be y sub 1 of x is equal to e to the 2x. So remember the general way with which we solve this problem. So remember, since it's second order, we know that our second solution, y2 of x, should equal some non-constant function v of x times y1 of x. And so in this case, we get v of x times e to the 2x. So we get that this relation has to be satisfied. And like we discussed last time, we can use this fact to alternatively solve the following differential equation, the form of which I now want to quickly double check to make sure I don't get this wrong. Sorry. V double prime times y1 plus 2 y1 prime plus 2 y1, or plus, y1 times p times v prime is equal to 0. Let me just double check to make sure I have that right. Yes, I do have that right. That's good. All right, so we can transform our equation into this equation, but only if it's in the following form. y double prime plus p of x y prime plus q of x y is equal to 0. So if we have an equation of this form, we can then transform this into this. So we do need to make the very quick adjustment to our current differential equation. We need to divide through by 2x plus 7. So doing that, I get the following equivalent equation. That looks like that. So now it's in this form. This is my P. This is my Q. And so with these two things, we can now actually just rewrite out this equation, knowing that we've made this substitution already. And so this gives us v double prime times e to the 2x plus now 2y1 prime. y1 prime is 2e to the 2x, so this would be 4e to the 2x. So that would be that term. That would be that term. Now y1 times p, that would be e to the 2x times this nonsense. Remember, don't forget to include the negative here. Notice this form has it plus p of x times y prime. So this would have to be minus e to the 2x times 4x plus 16 over 2x plus 7 times v prime is equal to 0. All right, we can do a little bit of simplification here. The first thing I'm going to do with this, however, just because I don't like looking at v double prime and v prime, I'm going to let u equal v prime so that du dx is equal to v double prime. I'm also going to divide through by e to the 2x to get the following equation. Du dx plus 4 minus 4x plus 16 over 2x plus 7 times u is equal to 0. And so now we've got a separable equation, which we can now solve. We can separate the variables u and x. So this is equal to du dx plus what I'm going to do, I'm going to multiply 4 by 2x plus 7 over 2x plus 7. So this would give me 8x plus 28 minus 4x plus 16. So this would be 4x plus 12 over 2x plus 7 times u is equal to 0. So this step, I just combined this fraction here. Now I can separate the variables and get negative du over u is equal to 4x plus 12 over 2x plus 7 dx. All right. So we can integrate both sides now. To give myself a little more room, I'll probably, guess I can start erasing. I want to keep the y1 there since we'll need to remember what that is. All right, the left-hand side of this just integrates to negative ln u. For the right-hand side, what I'm going to do, I'm going to rewrite this function. This is equal to, and this is almost sort of like a partial fractions thing. This is equal to 2 times 2x plus 7 minus 2 over 2x plus 7. So the goal here is to turn this into the sum of two fractions, or two numbers, such that the numerator of each of these numbers, or just basically that two terms that we can now integrate. This by itself we don't really know the integral of. So what I did is I kind of just said, okay, I want to get rid of the x terms in the numerator. So I want to get a factor of 2x minus 7. If I can do that, well, then maybe I just need to subtract off a little bit to make sure that I've not actually changed the value of the numerator. And this gives me the following two terms, each of which I know the integral of. So this would imply that the integral of 4x plus 12 over 2x plus 7 dx is equal to 2x minus the natural log of 2x plus 7. So now, we'll maybe give ourselves a little more room. We know that negative natural log of u is equal to 2x minus the natural log of 2x plus 7. This implies that u is equal to e to the negative 2x times 2x plus 7. So that's just doing a little bit of algebra. And so remember, this implies that dv dx is equal to 2x plus 7 times e to the negative 2x. And so now we just need to integrate this in order to solve for v, which will then allow us to solve for y. So this function here you can integrate using integration by parts. So first I'll sort of note the integral of 2x plus 7 e to the negative 2x dx. Be a little easier to break it up into the sum of two integrals because the second integral will be relatively straightforward. So for this integral here, we want to use integration by parts. So remember, the integration by parts formula says that the integral of u prime v is equal to uv times the integral of u v prime. I always remember this. This is the reverse product rule. All right, so I'm going to let we want to let u prime be the thing that either easy to integrate, maybe a better way to determine it in this case is we want to let v be the thing that is sort of eventually going to disappear by differentiating. So we've got our u prime and our v. U is equal to negative 1/2 e to the negative 2x. V is just equal to 2. And so using the integration by parts formula, this is equal to u times v, sorry, so that would be negative, v prime. So that would be negative x e to the negative 2x, so this would be u times v, minus the integral of v prime times u, so that would be minus the integral of negative e to the negative 2x. This is equal to negative x e to the negative 2x minus 1/2 e to the negative 2x. And so this is equal to negative x, and this will actually be equal to v of x here. Negative x e to the negative 2x minus 1/2 e to the negative 2x minus 7/2 e to the negative 2x. And so this last term is just the integral of this function. All right, so v of x is equal to negative e to the negative 2x times x plus 4. So I did this. Notice I can factor out an e to the negative 2x from each of these terms. At that point, I get x plus 1/2 plus 7/2, which is equal to 4. But remember, the solution we're looking for is equal to v of x times e to the 2x, remember, which is y1. And so we get negative x plus 4. But remember, we can take this solution sort of multiplied by any constant, and so I think your book just has it as x plus 4. That is, it's equivalent to multiply it by any constant we want out in front here. And so we can just kind of forget the negative and rewrite x plus 4. So that is another reduction of order problem. Like I said, a little involved, but good integration practice. So yeah, I think this trick is a good trick to remember. When I was working this out, it took me a few minutes to look at that and say, how do you do that? But always kind of remember that if you've got linear term over linear term, you can usually break it up like this. Integration by parts, always fun. So yeah, so that's pretty much what I've got for this week. There's more on that worksheet, so certainly if you have any questions on that, I always try to include a little more just in case we get time in class or if people want to specifically go over different things. If you have questions on any of that, let me know. Some of it actually does cover what's covered in homework 7, and so I'm certainly happy to talk about those, although we might end up talking about those later next week as well. And if you haven't taken quiz 2 yet, make sure, not quiz 2. If you haven't taken the quiz this week yet, I want to say it's quiz 7, I think, make sure to take that. So yeah, thanks for watching.